Hello everybody, my name is Justin and I'm going to be talking about quantum finite automata, which are also known as QFAs. For our agenda, I'm going to start off by discussing the various types of classical finite automata, some of which we have actually already studied in Fox and Cocoa. Then I'm going to introduce three different types of QFAs and compare their qualities to their corresponding classical counterparts. And then finally, I'm going to conclude by comparing QFAs to other quantum computing machines, such as quantum Turing machines and quantum pushdown automata. Classical finite automata could be characterized with a five-tuple definition. In this definition, Q will represent a finite set of states, sigma represents the input alphabet, delta will represent the transition functions that will change the state depending on the input, Q naught will represent the initial state, and F will represent the set of all accepting states. Later on, we're going to see that QFAs could be defined exactly the same way with this five-tuple definition. The three different classical automata are known as deterministic, non-deterministic, and probabilistic finite automata. An example of a deterministic finite automata is shown here in figure 1. You'll see that input of 0 will lead to one state, and an input of 1 will lead to another state. And it's deterministic. If you have an input of 0, you're guaranteed to go to this state. However, a non-deterministic finite automata, shown here in figure 2, shows how an input of 1 could lead to either here, P, or to Q. And so it's non-deterministic. You don't know where it's going to end up. And finally, a probabilistic finite automata is a non-deterministic, an NFA, with probabilistic state transitions. And these need to add up to 1. And as we'll see, a PFA is the QFA's closest classical relative. So one distinguishing characteristic that is seen in both classical and QFAs is the ability to read an input tape either one way or two ways. And although this may simplify some classical finite automata, two-way automata do not really change the computing power of the classical finite automata. And regardless of the type of classical finite automata, one-way and two-way, DFAs, NFAs, or PFAs, all of them only solve regular languages. And we'll see that this is actually not the case with quantum. Now we're going to start discussing QFAs. Informally, we're going to define a QFA as a quantum analog of a probabilistic finite automata. And this time we're going to be using quantum states as opposed to classical states. After an input string is read, the QFA is either going to accept or reject a word with a probability between 0 and 1. The first QFAs that we're going to discuss are called one-way QFAs. And unlike the classical finite automata that we were just talking about, one-way QFAs have less computation power than two-way QFAs, and so they're going to be discussed in separate slides. The simplest QFA that we're going to talk about is called the measure once QFA. The measure once QFA is defined with a five-tuple definition, and it's very similar to that of a classical finite automata. It's going to begin at an initial state, Q naught, and it's going to be constantly changed by unitary matrices. And these unitary matrices are going to be given by the transfer function for each input symbol. The unitary matrices will be applied one by one until the input string is completely read. And then finally, a projective measurement is going to be performed on the final state. And this projective measurement will decide whether the input is going to be accepted or rejected. And the probability of accepting a given string can be found just by applying all of these corresponding unitary matrices. And so measure once QFAs are actually only able to recognize a subset of regular languages due to the restriction of only using unitary matrix operations. And so they're actually weaker than their classical counterparts. Another variation of one-way QFAs is the measure many QFAs. And rather than measuring once at the end, as done in the measure once QFA, we see that the measure many QFA will perform a projective measurement after every time a unitary matrix is applied to the current state. The outcome of the measurement will fall into three categories, and these categories are accept, reject, or continue. And if the outcome is either accept or reject, the QFA will halt and end. And if it's continue, the input string will continue to be read. So therefore, the measure many QFA might actually end the computation before the full string is read. And although the measure many QFA is known to be the more powerful than the measure once QFA, it still only recognizes a subset of regular languages. And one-way QFAs are found to be less powerful than their one-way classical counterparts because of the subset of regular languages as opposed to all of the regular languages. However, we see that the one-way QFAs in some cases are able to be exponentially more space efficient than their classical counterparts. Now we're going to be talking about two-way QFAs. Two-way QFAs perform similar to one-way QFAs with the addition that the read head is now able to move left and right as opposed to just right. And this difference will actually allow the QFA to recognize more languages than the one-way QFA. Not only can the two-way QFA recognize regular languages, but now it can also recognize non-regular languages. And this means that the two-way QFA is more powerful than its classical counterpart, which is the two-way classical finite automata. Finally, we're going to be comparing QFAs to quantum pushdown automata and quantum Turing machines. Quantum Turing machines are the most powerful of the three, and QFAs are the least powerful. And this is not surprising because the same trend can be seen when comparing classical Turing machines to classical pushdown automata and to classical finite automata. And this picture on the left shows the comparison in computing power between the three machines. And this picture on the right shows the computation speed for each of the three machines to solve a specific language. In this picture, we see that quantum Turing machines outperform the other two, while the QFA and the QPDA are very similar in computation time. And the QPDA will have similar computation time to the QFA because of the extra time it takes to add and pop to the stacked memory that is associated with the QPDA. And thank you for listening. Do you have any questions?